Well, thank you for joining us today. I'm Renee Smith from Toluna, and this is Ziad Elmously, my colleague. We're both on Toluna's innovation team. We're going to talk today about synthetic boost samples and how to unlock deeper insights, so make analysis and deep dives possible that would not otherwise be possible due to low base sizes. We're just going to do a quick overview and why synthetic boosts, and then we're going to talk about some lessons learned, and Ziad's going to come in there and show us some comparisons and why the model you use matters and so forth. So let's jump right into it today. In terms of synthetic data, we're talking about data that's been produced for the purposes of populating a separate data space that mimics the statistical properties of the real data. So it starts with real data and creates artificial data. There's a couple of approaches. One's being called in the industry synthetic boost. That's what we're here to talk about today. The other's being called synthetic personas. That is also an area Toluna is working in, but it's not something that we're talking about today. And then in terms of a synthetic boost sample, the distinction between those, one of the distinctions between those two things is that we're referring to samples of tabular numeric data, so not the text answers, for example, and a process of amplifying the signal that's in a small subset of sample to be able to bring it into higher resolution, higher focus. There's some different modeling approaches to creating synthetic boosts, and that's where Ziad's going to definitely come in and talk about some of the comparisons. So first, I'm going to talk about Toluna's approach to generating synthetic boost samples and then talk about why we want to do this. So it all starts with real-world data from a project or from a prior project or from a database, for example. And we're going to fit a model. In our case, we're using what are called Gaussian copulas. We're going to fit a model to that structure of the real data. So it's not a model that has independent, dependent variables. It's taking some of the elements about means, distributions, correlation structure, taking the data structure from the real and trying to mimic that. The generation of the synthetic data in Gaussian copulas, once you create the copulas, you're sampling from there, from a joint distribution. And then it's also very important to assess the performance, and we're going to do that and show you that it's important to assess it on multiple dimensions, so more than the mean. Why do we think that synthetic boosts can be useful? Well, at Toluna, we think that the value lies in helping clients in unlocking additional insights that can help clients make decisions that they wouldn't otherwise be able to make. So, for example, you may run a habits and practices, say, a foundational type of study. You know, you knew in advance that you wanted to look at certain subgroups, and then you see something in the data where maybe there's only 50, 75, 100 people, and you'd really like to be able to drill down into that a little bit more. This is a way to extract additional insights without, or from the data that you've already collected and without having to go out and recollect more information. So when we are talking about unlocking the additional insights, we're actually talking about drawing the insights completely from a synthetic sample. So in the place where we see the most value at Toluna for synthetic boost, it's being able to unlock additional insights by focusing, whether it's key driver, factor analysis, cluster analysis, Gabor-Granger, whatever type of additional analysis you want to apply, unlocking those insights from the synthetic data. So we've done this with some clients. This is an example. Toluna has many types of clients. This happened to be an agency client. They wanted to be able to identify the impact of different product characteristics on appeal for a very small segment that was in the data set. So the base size for that small segment was just n equals 55. So whereas, you know, they were comfortable taking a look at, for example, you know, top box or top 2 box score from there, they couldn't really do much more with it. Toluna used its approach, which we happen to call HarmonAIze Boost. It's not a sales pitch, but that's what we call ours. We used it to generate a synthetic boost of that 55. We boosted it to 1,000 synthetic records, and we did the analysis, the deep dive analysis on the 1,000 synthetic records. In this particular case, the client was interested in things like a product segmentation, and they found good results there. They were also interested in some additional analyses like penalty analyses, which, by the way, as you know, can often be like an inverted U, and so having that nonlinearity. And we found that the results, since they had real data to compare to, we found that they would reach the same business conclusions, and the segmentation results were particularly, correlations were very high. So we've seen success with this, and what that allows both Toluna and its other clients to do is to be able to sometimes accelerate decision making. So for example, in a tracker, maybe you would normally have to wait 6 waves, 9 waves before you had enough data on a particular brand. Now you can boost it and make some decisions about, say, marketing communications and so forth sooner. So a lot of reasons why. For us, this is not about filling gaps in a sample. We think that synthetic personas and other approaches are going to be the most likely use case there. So I'm going to now turn it over to Ziad to actually start talking through some of the lessons that we have learned as we've gone down this route.
So in the next few slides, we will empirically compare the performance of the key methods for generating synthetic data, and we'll do so by quantifying their ability to replicate the moments and distributions in the real data. So starting with the SMOTE, SMOTE is short for Synthetic Minority Oversampling Technique. It uses K nearest neighbors to generate new observations in the minority group while keeping the number of observations in the majority group the same. So we consider SMOTE a special purpose method for correcting the imbalance of group representation data sets. The next method is TVAE, stands for Tabular Variation Autoencoders, and it consists of 2 neural networks, an encoder and a decoder. The encoder maps the input data to a small number of dimensions, whereas the decoder reconstructs the original data from that small number of dimensions. And then there's the CT-GAN, which is the tabular version of conditional generative adversarial networks. And it is a type of artificial intelligence that uses 2 competing neural networks to produce synthetic data that are highly realistic and indistinguishable from the real data. So the generator creates synthetic data that are as realistic as possible, whereas the discriminator evaluates the data to determine if they're real or synthetic. And the generator and discriminator networks are trained concurrently, and the generator gradually learns to create more realistic data. And then there's copulas or Gaussian copulas. And Gaussian copulas use multivariate normal distributions as an engine to generate synthetic observations that comply with the individual and bivariate distributions in the real observation. So they're grounded in statistical theory, and they do not involve artificial intelligence or machine learning. Last but not least are diffusion models. They work by iterating across 2 steps. In the first step, they add random normal noise to the input samples. And then in the second step, they learn to denoise these samples. So in the process of noising and denoising the samples, they create observations that again mimic the characteristics of the real observations. So the table here depicts the means for 2 ratings on a 1 to 7 scale and 6 binary category attitudes using 1-2 coding, where 1 means yes and 2 means no. And we report these means for the real and synthetic data generated using these 5 methods. So in general, we observed that the synthetic methods mimic the real data means. This is further confirmed by the mean absolute deviations across more than 500 variables. With the smallest mean absolute deviation of 0.01, the Gaussian copulas fit the real data closer than the other methods.
And Ziad, it's
So,
probably worth saying that the diffusion model does pretty well with continuous variables and less well with binary. And then maybe just the other thing to add is that we're using the kind of basic, not basic, I would say classic applications of, say, GANs and diffusion for tabular data. There are ways to mix and match these. So if you hear that another vendor is using one of these, perhaps they have mixed and matched in a way that would optimize it further, but sort of just out of the box, the copulas are definitely doing better here.
so it's possible to combine the CT GANs with the copulas, where we reduce the dimensionality and then use the copulas to mimic the distributions of these smaller number of dimensions. So there's advantages to mixing and matching. And the diffusion models come in quite handy when we try to improve the predictive accuracy of classification engines or key driver models, especially on test data that are not used to train the models. So we talked about replicating the means, but the real criterion is the ability to replicate the patterns in the data. And one way to measure the patterns in the data is to use the correlation matrix. So to compare the correlations of the real and their synthetic counterparts, we proceed in two steps. In the first step, we extract the upper triangular or the lower triangular matrix in the correlation matrix, and then we map it to a single column of numbers. And then in the second step, we correlate the two columns of numbers. So this amounts to a correlation of correlations. And with a correlation of correlations of 90%, the Gaussian copulas clearly outperform the other methods. Now, in assessing the correlation of correlations of 99% for SMODE, we should be cognizant of the overlap between the real and synthetic data sets in the application of SMODE. So the synthetic data set includes all the observations in the real data set plus new observations in the minority group. So in a sense, in comparing the performance of SMODE to that of the other four methods, we're comparing apples and oranges. So as is often the case, there's no free lunch. By virtue of using synthetic data to boost the real data, we add noise. And this manifests itself in the lower efficiency in the hybrid sample, which includes the real interviews and the synthetic boost records. So we recommend against using the standard statistical formulas like t-test to report confidence intervals for the central tendencies and other statistical measures. Instead, we recommend simulation-based methods, and these include the bootstrap and jackknife. So the simulation-based methods will calculate the correct confidence intervals. These confidence intervals will be wider than those calculated using the standard methods. Otherwise, we may incorrectly conclude that concepts are different or means are different across subgroups when in reality they're not. This is known as the type 1 error in statistical jargon. For that purpose, we conducted an experiment using a hybrid data set, again, that combined the real and synthetic observations. We used the bootstrap method with 500 iterations to calculate the empirical 95% confidence intervals, and we compare them to those calculated using the standard formulas. And as expected, the confidence intervals reported using the bootstrap method are wider than those reported using the standard methods, but they're more accurate in that sense. And in comparing the ratio of the confidence intervals using the bootstrap methods to those using the standard methods, we use a data set with 1,000 records and 65 variables. And we observed that by and large, so in 75% of the variables, the confidence intervals are 1.4 to 8 times wider than they would be otherwise, and 3 times to 23 times wider for the 25% other variables. So the conclusion is use simulation-based methods when you report confidence intervals for hybrid data sets.
Yeah, and just a reminder that in terms of unlocking insights, our approach is actually that we analyze the synthetic only, so we don't face this problem. I mean, that's not the only reason we do that, but we don't face this problem because we analyze the synthetic only. But we did want to just point out, and we're not the first ones to point this out, but I think it's important for people to realize that if you are going to create a hybrid sample and you pretend the synthetic are real, then you're going to be thinking, as Ziad said, that means or concepts are different when in fact they aren't. So lesson 3, just real quickly, there are reasons to use, even though we've shown that the copulas perform best on this data set and we've shown it on other data sets, it's not one size fits all. So there are specialized uses that Ziad kind of mentioned for SMOTE. Like if you're building a training data set and you need to balance it, SMOTE is a great way to balance that training data set. CT-GAN by itself doesn't seem to perform very well, but we do know of some literature that combines GANs with copulas, and so we're investigating whether there's some improvement there for mixing and matching. And then we're using copulas more generally, whether we want to boost the total sample, perhaps it's B2B and you can only get 100 of them, or whether we want to boost and amplify the signal from a subset of the data. So just to conclude, we thank you for your time, but we do want to just kind of, remind you what we've been through. So the model you use matters. So we think it's important that companies that are offering these capabilities, actually state which model they're using, and also that we start to look beyond the means, that you look at things like correlations, or in some cases during proof of concept, we've been, pilot tests, we've been showing clients, hey, we applied a driver's analysis and here's your parallel real versus synthetic. There's no free lunch. There's always trade-offs there's always trade-offs in information, the same way that you can't use the standard errors in weighting. You need a different t-test formula, I should say. It's a similar situation here. And I think it's also important that you saw the range of how wide they can be. That's quite a big variation. So we really need the bootstrapped errors. And for us, it's about unlocking insights. We think the value for boosts, I know a lot of people are excited about them for filling gaps, but I think we'll probably see that more and more clients will come to see that the real value is in unlocking these additional insights from data that you've already collected. And it can be data from a year ago. It can be a foundational study you did a year ago. We can still unlock some insights there. So we would say work with companies that are being bold, but that are also being thoughtful and systematic about when and how to use these methods. And we thank you very much for your attention and look forward to answering any questions that you might have during the Q&A.
I'm going to start with one from my side. Probably the most talked about use at the moment is to use it as boost, where people have got maybe a slightly lower sample of young men. You're moving very much in the direction of now focusing on the synthetic data to unlock insights. Do you have something against the boost use, or is it just that you think that this unlocking insights is a bigger use or a stronger use?
So I would say that using the synthetic is the boost approach. So let's not get caught up on the terminology, but the main challenge we have right now is that we're not seeing people understanding that to use it in other ways, you do have to re-estimate the standard errors. And so for us right now, I think that we want to make sure that clients are getting the right sorts of inferences. I think the other thing is that we're a company that's actually going to be playing in both spaces, and we think that the synthetic personas, because they can answer things in real time during field work, are probably the better use for filling the gaps. Yeah.
Now, one thing you mentioned briefly, and perhaps we could explore a little bit more, is which types of data respond well to this. So we have binary data. In the old days, that might be gender, male, female. And so you get a maximum standard deviation between the two because all you've got is 0 and 1. And then we have maybe a net promoter scale, which has got the 11 points, 0 to 10, and is going to behave differently. Maybe we've got some genuinely continuous data like income that we're working with. What differences are you seeing in the techniques when we start moving around from these different types of quantitative information?
I'm going to let Ziad take that. Ziad, when you answer that, maybe you can also talk a little bit about measurement error.
So these are methods tailored for tabular data. So we haven't delved into images or other types of multimode data or open ends. Although in principle they can handle these types of data. But generally speaking, the idea behind these methods is to first capture the patterns or the correlations in the data, and then once we do that, so basically we're mapping out the density function in multiple dimensions, and then once we do that, then we oversample in areas of high density and undersample in areas of low density. So it's think of it as a nuance weighting technique where we don't actually replicate the observations, we generate new observations. And that, by definition, lends itself to continuous variables. So, and Renee has made the point before, it's easier to capture patterns in continuous data like ratings on a 1 to 7 or 1 to 10 scale than it is to capture patterns between binary variables or categorical variables like income or gender or age groups and so on. However, they perform well in mixed type data. So in principle, these methods work for all types of tabular data, but they seem to capture the patterns or distributions better for variables that are measured on a continuous scale.
So have you explored using sort of more logistic ways of thinking on the binary variable? So instead of this is a 1, what is the probability that this is a 1? Might then move you more into continuous variables in those binaries.
Correct. So a lot of these methods are based on correlations, right? So like with the Gaussian calculus, you basically measure the correlation and then use that to generate observations or draws in multiple dimensions. And the correlations are harder to measure, are not really tailored for binary variables. There are other methods that, similar to chain regressions. The difference here is that the data are not necessarily missing. So you basically cycle across the variables, and for every variable, you build a model. You predict it using all other variables, and the type of the model depends on the nature of the variable that you're trying to predict. So you may use methods like gradient boosting machines or logistic regressions or whatever, if they happen to be binary, or a CART or linear regression if the variables are continuous. And it's a matter of iterating across these variables a sufficient number of times until you achieve convergence. So there's specific methods that more explicitly account for the nature of every variable. And then circling back to the traditional options like SMODE, there are certainly variations of SMODE. So SMODE was originally uses KNN initially. So again, these work better with continuous variables, but there are certain implementations of it that we currently use that are tailored for continuous variables.
Super. Now, I've got a question about tracking. And it was one of the things you highlighted, Renee. I'm going to split it into a couple of pieces. So if we think about brand trackers, how might we apply this? And then if we're thinking about CX trackers, so we're getting 30 interviews a month from each of 1,000 McDonald's, how might we apply it? So those are two quite different sorts of trackers.
Yeah, so one thing to think about that applies in both is you don't throw away your research fundamentals. So you need to think about whether you would be willing to, with the small data you have, would you be willing to look at, say, like a top 2 box, or would you say, oh, wait a minute, that might not be fully representative, because this is not this is going to take the structure you have and it's going to mimic it. So if you would say, well, say in customer service, if you say, well, no, actually, the problems that company was having 6 months ago in customer service are not the same as the problems they're having now, then you might not want to put those two together and then boost them, for example. In a brand tracking situation, again, in any kind of tracking, you should think about whether there's been any structural changes before you put responses together. But we feel pretty comfortable. The one thing that we're looking at right now that we don't have fully worked out is in our particular metrics for brand tracking, we have a composite score. And so we're trying to understand, should we create the individual metrics and then put them into the composite the way you would do in the real data, or should we try to create the composite synthetically without that intermediate step? We think it's create the elements and then create the composite. But so there's different nuances. But I think the other model to think about for tracking is, and this could help with some, if you think there's potentially a structural, or you want to mitigate structural things, you could potentially think of it as going out and collecting. Let's say that you've got a monthly tracker. You could think about every 2 weeks collecting part of the data on the KPIs. So you had some fresh data on the KPIs, combining that with the month before, and then boosting to like get the rest. You'd have sort of a boost and a little bit of imputation, I guess, in that particular case. So I think there's a lot of ways in which not just boosts, but actually personas are going to open up new ways that we think about research design.
And we've got another question in the chat stream. What's the minimum quote real data that you'd feel comfortable with before generating synthetic data?
Yeah, we've done a lot of looking into this. We're not comfortable right now to go below 50. The place where we're still investigating is whether we can go below 50 is sort of like in the chronic illness space. So we're wondering whether the homogeneity of certain subgroups might mean that you can go a little bit below 50. But in general, consumer research, we don't go below 50. And of course, if you've got 100, we'd love to have 100, right? But we could do it with 50.